with the seasonality stuff, we're trying to factor that out and smooth the data over time. And you can run the dummy, depending on what type of analysis you were doing, yeah, the coefficient would be first quarter, second quarter, third quarter would be kind of 4 different lines possibly coming through. And you could see which one was significant or insignificant. And I think they kind of did that with that problem, didn't they? Wasn't the fourth quarter was significant, but the other ones really weren't or something? The biggest coefficient. Was the significance different though too? That's okay. Don't even look it up. But you got it conceptually. So it's like if quarters 1, 2, 3, and 4, and quarter 4 was significant, the t-stat gave us a significant result. But if the other ones were insignificant, again, the coefficients might have been had numbers, of course, with them. But if they're insignificant, what do we treat them as? If a coefficient has a t-statistic that shows that it's insignificant, what do we assume that coefficient to truly be? 0, right? It's not significantly different from 0. That's our test that we're always doing. And so even though those dummy variables are in there, they're not having an impact. Kind of some simple ways to test for stuff like that when you start diagnosing things is to drop that variable. And if you drop that variable, you won't have much of a drop in your r-squared. So you can start to see that dropping an insignificant variable is not too big a deal because it's insignificant. And it also won't change around some of the magnitudes of your coefficients as well. Okay, so let's see, what else do we have to read more on this thing? Okay, so let me be quiet for a moment and just go ahead and read through this 1, 2, 3, and 4. Yeah, just on the sheet, and then I want to kind of hone into number 5 and see what you think about that. Does that make sense what they're saying in number 5? What are we effectively doing with number 5? Non-residential equals 1 minus residential. In the column of data, what are we effectively doing? Imagine that column of data. I can't remember, is the data on here? It is, right? I don't think it's on here, but if we go back to our data set, the very first thing here, the main. Yeah. There's your raw data. What is that new variable, non-residential equals 1 minus residential, really doing to this column of data? It's just flipping them, right? It's just taking the 1s and making them 0s, taking the 0s and making them 1s. And so all he's trying to show there is that we're kind of switching the baseline, but the result, of course, you wouldn't expect that to make a difference, right? A rose by any other name smells as sweet. So if I label this a 0 or this a 1, should you be worried about what it is or what the results are? And the only thing you need to be worried about is how you interpret the coefficient. because now we've switched which one's getting the weight of 1 and which one's getting the 0. And that's what he was talking about with the baseline case. So if you come back to that now, the above results are based on having non-residential schools as the baseline scenario. So by giving the residential schools a 1, our baseline was kind of the non. And so we're saying, what is the impact of a residential school? And we get this negative. By flipping it around, what happens to the sign? It just switches, right? And so now the interpretation is that this would be the non-residential gets the 1, and we're saying, hey, if you're a non-residential school, look at, you get that kind of effect, that kind of positive effect. See what I mean? So it's just on how, which one gets the 1 changes the interpretation, but the magnitudes, the t-stats, all of that, of course, would be insignificant to how we organize the data, whether it's 0 or 1. It's all in the interpretation. Okay, any questions there? All right, multiple dummies. Let's go ahead and read this. Okay, starting up top here. First thing is, urban has a negative 0.75 roughly, right? That's our 3/4 of a slice. But should we care about that? Right, the t-stat's too low, so that is insignificant from 0. We talked about this a bit. A different way of thinking about it is that our 95% confidence interval around the 0.75 coefficient includes positive numbers too. So if we were to graph out, I don't think it's done here. Oh wait, maybe it is. Yeah, we got it here. So to be 95% confident that that is going to stay negative with a one-tailed test, we can't be 95% confident. So that interval, if we look at the range of possibilities, goes from negative 1.9 to 0.43, completely opposite effect. So we're not confident that that's going to stay the same.
Did you say the same thing about tuition at this point? I mean, I think we talked about it a couple of weeks ago. I think it actually could be fairly statistically significant, but it also has an upper and lower that are positive and negative.
Yeah, this is probably real borderline, and yeah, that's kind of being reflected here. And I don't remember, was that one? I think it was significant with a one tail, right?
Yeah.
Yeah.
It was like 1 point.
Yeah. But yeah, that ends up getting us into this positive range. But if it clears the t-stat, we get the blessing from the actuary gods, then we you run with it. So.
And for it to be there, it just has to be greater than 0?
Yes, that's the idea of the one-tail test on how significant.
Greater than your critical T.
Yeah.
Right.
Yeah.
This is the statistic that it actually is. If we go back to that T table, that'll fall in one of the ranges depending on the degrees of freedom. Degrees of freedom are determined by not the population.
The amount of different things that you have are I'm trying to think of it. I can't even think of it.
The sample size.
You.
The population is usually the.
Sorry, yeah.
So the
I was
population is what we're trying to get
Sample.
inference
Sample.
on.
I was
And
trying
then
to
the
say
sample
the list of things
size.
that you were going with, and I knew that did not sound scientifically correct.
Right.
And then subtract out the amount of variables.
Variables and with an extra one.
And we actually, this is probably a bad Venn diagram. I mean, we'd actually like to make sure that the sample size is randomly distributed, but whatever. We got a smaller fraction of the population in the sample size, and then it's degrees of freedom is sample size minus
Categories.
the number of variables that we have, the number of independent variables. Yes. And then the one for the intercept. Okay. So here we get the high T statistic on the dummy. What did you think of the partitioning at the bottom?
I mean, it makes sense to include it that way. It would almost change the way you run your regression because then you just have to do your categories. You have those things, variables.
What are they trying to say here with the 3 baselines? Somebody other than John here. What are you picking up from that? I mean, we're yes. So you're always, so you've got, what's kind of weird, because sometimes when I've done this, you're always thinking, I've got 3 things, I need 3 variables, but you actually only put in 2, because the other one is your baseline that you can't really see. So it seems like in order to be doing something, oh, I've got these three areas that I want to investigate, boom, 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 then I better have dummy variables for all 3. But you don't do that because your baseline is one of those. Whichever one's getting the 0 is one of those factors. And so that's how you get your 3 is by having only 2. 2 of them show up on your output, and the baseline is the one without. And so you're capturing all 3 by only including 2 in your regression. That's what's kind of weird.
Baseline is suburban in this case.
Yes. And once you, I mean, it's just kind of weird at first when you get into multiple dummy variables of partitioning out multiple sections, because when we do it the first time, we're really doing the same thing. We just maybe didn't, it wasn't quite as obvious, right? We had 2 residential, non-residential that we were looking at, but we only included 1 in the regression. We only had the residential was the only one included. So it's always just -1 of what you're mentally thinking of the 3. Okay. Is that good on that? These are just kind of little tidbits on putting them together. All right, let's run to omitted variables. So I shrunk down my screen to get them all up. I don't know if that's too small here or not. Let me give you a quick broad brush before we read, just a couple comments. So a lot of times we're worried if we omitted an important variable. And so this kind of looks at the potential biases that you might have if you left out a significant variable. Yeah, well, either on accident or because you didn't have it. And if you didn't have it, it's captured in the intercept term. So you can kind of think if you have a variable that is not there, and maybe you need to find a variable to make it suit its needs, but what is the impact on your coefficients and results, it's not good. If you have a missing significant variable, then it's going to potentially distort or bias some of the coefficients that you have included. And so that's kind of just to tee you up a little bit. Go ahead and read this through. In fact, read the whole page. It's really just this middle part, and then he's got the tables here for you to review. So, what do you see going on here? Are you getting the... I want to take a look at the sizes of the coefficients and their significance. So, here's the regression ran without the significant variable. What can you say about the magnitudes of the coefficients? Are they a lot different or a little bit different in your opinion? Did they change wildly? Did they change signs? No, right? So those are the types of things that you want to look at. Chelsea?
Well, I was just going to say, if you look at the T-stats will more significant.
Right.
And so maybe they are more significant, they are a little more significant.
Yes. So when economists do research papers, in theory, in a perfect world, you're like, oh, let's run a regression and see what the results are, and then the results are what they are. But that's not what really goes on. We kind of really are diagnostic about it and say, suppose I leave off one of these variables. And we saw this in the wine thing, right? You had the whole table of multiple regressions run, where we left some out, we put some in, we kind of experimented and dabbled and look at the table. When you publish your results in your final paper or whatever, whatever it is, when you publish those results, yes, my voice tends to carry.
I know, she just
you will state that maybe in the paragraph that these results were robust to checks. We did robustness checks on the variables, whatever, and that robustness is what we're kind of seeing here, is that I've dumped some variables and the magnitude stayed pretty close. They didn't flip signs. That's especially what you'd be concerned about, is like flipping signs. Then there might be some heteroscedasticity or some other problems in the data. And then we also see, as Chelsea pointed out, the t-stats get better, right? So we have a stronger t-stat, so we can be even more confident perhaps about the sharpening or fine-tuning that this coefficient is actually better than this coefficient, right? And then you see the dramatic drop in R-square. So R-square is the overall explanatory power of all of our, taking as a group, all of our independent variables. How well do we explain the variation in our dependent variable? That's our R-square statistic. John?
I was just kind of curious, how much do you need explained before you get something published one way or the other? Like, I'm doing like a real research assignment.
You know, that's across the board and depends on the type of analysis. So you start to get a feel from your literature review. If there's like published papers that have lots of R-squares around 50% or 60, then you kind of use that as a guide, that there's a lot of variability, there's a lot of variables that we can't get good proxies of. And so the R-squared might be relatively low. So you kind of go from experience on what other people have done. Otherwise, getting into this is pretty high if you start getting into that level. But I would say that's what you'd use as your benchmark, is what other previous research has done that is maybe similar in that industry.
Just curious because it's helpful for our papers.
Yeah. And that's the type of comment you would make in your paper about the R-squared. So the R-squared for my paper, or for my results, ended up being 0.88. Previous research indicated R-squares ranging from 0.75 to 0.9. You know, so we felt like this was in a reasonable range. Something like that. Just kind of looking at the previous data and putting what it is and what that is, because that would be a good point. If you kind of have a low R-squared, I've seen that in other papers where they kind of have to justify why it's low, because kind of at first blush, an outsider looking in would say, oh, this one's kind of crap. So you might have to justify that. Okay, any other questions on this? Let's see, did I hit all the bullet points? We talked about standard error estimate and the patterns, yeah. Just that you can kind of see that bear out here with the dummy variables. The author cut and pasted the observations on whether they were or weren't. And so with it in, with the residential dummy variable in, then we see the residuals getting better. Just reinforcing the explanatory power that it's giving us, that it's tighter. Okay. Let's see, I think I wanted to do this one last. Just kind of a quick review of R-squared. So if you just press the number 5 tab, we've been talking about R-squared. Kind of a fun fact, or something that you should know, is that you can add any variable into a regression and you will have an increase in your R-squared. So it's not always good to just have extra variables. What the author did here is put in what they called garbage, because it was a random variable. They just added a column data that was a random variable between whatever. I can't remember if they told us here. They probably did.
They literally just use a random.
We're not going to do the exercise, but they had the computer generate a random variable and said, oh, how does this variable do for predicting? They ran the result. We get the coefficient of 0.17. Ooh, this sounds encouraging. The t statistic is 0.25. Is that close to 2?
Or not.
Not so much, right? So we got that rule of 2. So it was insignificant, absolutely garbage, truly in all forms, except that the r squared did indeed go up. So the r squared for this regression is 0.884879, and the r squared for the previous one was a little bit less. So this r squared with the garbage variable went up by a little bit. And so then he runs you through an exercise where you can just prove it to yourself, create your own random variable and do it. Yeah, it's always, the point with it is that it's always going to go up. So we don't really test the significance of this going up, other than that's part of why we have the adjusted r squared.
And also
that it was an insignificant up, and in fact, it actually went down, the adjusted r squared.
And the standard error also went up.
Yep, and standard error, the estimate went up, which causes our coefficients to also decline in significance. This one, does it show at the bottom? No, it shows something.
It shows the garbage.
Okay, any questions on that? Just wanted to point that one out to you. For r squared. All right. I guess the last thing, this number 8 just points out that that adjusted r squared makes an adjustment dependent on the number of independent variables. So it counts against you as part of the calculation the more variables you throw into it. And that's why that ended up going down. All right, so I want to get into growth next. This was part of our chapter we just got out of.
There you go.
Well, not on a page. It's on 13, yeah. Excel app number 13, growth. Yeah, it's a totally different app, so you can close out of that app. Okay, so the homework problem that you just worked through looked at forecasting techniques, and one of those techniques is to just simply use the variable itself and project it into the future, right? Kind of the simple forecasting idea. And we had different ways to think. Let me try to motivate this with a little bit of an example. I saw from your book too. So if we have, actually, no, I can't do that. I was going to say I don't have, now I don't have Taylor on. Oh wait, I got to do it over here. I knew there was some way I could do that. All right, Taylor, I'm going to get you fixed up here for a sec. Stop share. Okay, so if we're looking at sales data over time, actually, I'll tell you one that we're looking at. Let me be a little more specific to OU. Enrollment. So how many new freshmen are we going to have, new incoming people, this fall? And so we can look at the number, maybe the variable that we'd measure is how many deposits do we have is one thing that we track here. How many of you are in enrollment? Are any of you in the enrollment area?
Admissions.
Yeah, admissions. And so are you familiar with that
Yep.
tracker? So we keep track of how many deposits, right, at a different point in time. Do you know what? Are you doing that right now?
I'm not specifically working with deposits, but we try to get them.
Because I know they share that with the team, right? How many deposits we have, or when they have meetings. I don't know if you're in with the advisors. So here we are on February, and then we got March, April, May, June, July, and school starts, right? We got August. So where are we going to be at in August? And so if we're tracking deposits as our variable, we can look at, you don't happen to know how many we have right now, do you?
No.
Okay. Let's say that we've got 100. That's just pulling a number right out of the air. And then in March, we have 110. Right? So we can kind of start to plot where we're at and how we're going to be. And this is week by week data, I believe. So there can be lots of data points in between of where our enrollments are. So it might flatten out, right? If we're kind of riding the roller coaster, it might look like this. Oops, won't go backwards on itself. Wherever we're going to be. And so at any point in time here in February, we're kind of questioning, well, where are we going to be next month? What should be our goal, right? What's our forecast of what we predict is going to be? There's different ways to do that. So one of those was to take an average of the previous 3 weeks, maybe. What's it going to be next week? And maybe we can talk in terms of the flow of deposits, the number of deposits, or are we predicting the aggregate number of deposits? So this is, I was kind of saying 100 to 110, or from a week to week, do we look at the first difference that we picked up 10 people, we picked up 5 people, we picked up 4 people, we picked up 5, 4, 3, 2, whatever that series would look like. So we can start to carve up the data on whatever we think would be meaningful as far as meeting whatever our objective is. This growth rate model looks at, well, what is the rate of growth? How do we calculate? If we're using the growth rate, what is it going to be next time period? The orange is our question mark. And is it appropriate to average this number at the beginning of the time frame and this number and take the linear average and say that this one's going to be a linear projection of that trend, right? Our trend is upward, and then we can predict what it's going to be next time period. Yeah, if it's following the trend line. But check this out. If I instead think, well, what happened back in February? Well, that's irrelevant. What have you done for me lately? And lately, the trend seems to be the green line here, which puts us off at the green dot is the better prediction of what we're doing, right? So all of a sudden we start getting questions of where should we start the average and how should that look like? What should that look like? Is it relevant to take the whole data series to look at that trend? It all depends on the question you're asking, okay? So back to the app now. I thought it was kind of funny. This is similar to what we did in the wind blowing or something. Let's see. Or ghost. The ghost of the admin building.
It's actually Max.
So, Max wanted me to share with you something now that you brought up Max. He wanted me to share with you guys that the work that he did during the capstone was really influential for his job interview process. The stuff that we did with learning Excel and kind of getting some of these concepts paid some dividends. He didn't tell me exactly when and how. I mean, we had a longer conversation, but just things that he was able to talk about, maybe convey himself and have a little bit of confidence with Excel and with just quantitative things in general, made a good impression, and he got a couple different job offers that he's pursuing. And I think I actually need to follow up with him. I think he went with the financial. He was going to work at American Century, I think, is where he was leaning. He already had a job with Target, and they're lined up, and then he had another offer come in from American Century doing some investments. So that was cool. So, anybody remember this from yesterday? Does it look kind of similar, right? So we got, except for Taylor, this was in investment finance class. So this is our present value, future value formula. So we've got the future value that we're trying to predict is a function of what it was before times the growth rate, if we're thinking in terms of growth rates. Like if you want to estimate what's the rate of growth, what's the rate of change, we can use this basic growth rate formula. Why don't you guys go ahead and read this down to, I guess give it a quick read down to this line right here. Okay, so first of all, what are we trying to estimate in this formula? It's said here, I just want to verbalize it out loud so we're all on the same page. What are we trying to estimate? What's our objective? The actual growth rate, little r. So we can't get r in using our regression analysis because this is a nonlinear function. So we are going to use mathematics to transform this nonlinear function into something that we can slam into Excel using linear regression. So we're actually modifying it using mathematics. All of this is legit, proven by people smarter than me with being able to prove formulas and stuff, right? So we get, by taking the log of each side, and we'll get into the natural log, you get the log of this thing is equal to the log of b times t. The way the natural log works with the transformation is that t now comes down in front, natural log of 1 plus r, and now we've got this thing into a linear form that we can slam into Excel. And how we do it then is we just pick off the pieces of simple slope-intercept form, just like we were doing before, or conceptually we're thinking of it that way. We transform our data set into, here's Merlot sales. Now we just literally calculate the natural log of that number. And now when we slam it into the regression, we're going to be using this column of data. And after we do that, we end up getting our coefficients and our predictions. We end up pulling off the pieces that we wanted to get. So all we have to do is run a univariate regression where the dependent variable is log y, the independent variable is t, and the growth rate r is obtained from the estimate from the regression. And so notice there's one little transformation here of whatever that parameter is, d. We have to undo the natural log, which is the e deal, and subtract 1, and we get our rate. The subtracting 1 just comes because this was 1 plus r, and now we want r all by itself, so we put the 1 over to the other side. And so it just we kind of retransform the coefficient back into what we were looking for initially, which was the rate. So this next piece, I'll just kind of gloss over that the log and the natural log end up being, you can do it either way. It's just a little bit cleaner to do the natural log. And if you click on this thing, he jumps you a number of columns over just to kind of give you the feel of what went on with the log and the coefficients. So not much with that one. He just kind of showing the differences. And then he's got that seasonal app that goes into all the more detail. So click return back to the main document. And if you go into the log versus natural log, second tab over. This is what your regression output looks like. And the main one I wanted to show you was just like our other regressions we did, time gives us the D, or that's our parameter we're looking for.